Welcome back. In this part of the session, we are now going to learn model performance measures, ROC, AUC, rank order table, KS lift chart. We have already learned ROC, AUC in our classification tree technique. When we built our classification tree on balanced data set, we used classification accuracy, and then we moved to unbalanced data set, and then we had learned ROC concept, AUC model performance measure, sensitivity, specificity, all of those. So I'm not going to repeat the ROC AUC part. I'm now going to jump to rank order table, case statistics, and lift chart concept. Rank order is often used as one of the most important model performance measure to find out how good is our model. Reason being, rank order table helps you ascertain how good the model is able to separate the yes class from the no class, the responder class from the non-responder class, the attritor class from the non-attritor class. End of day, when our target variable is dichotomous, when our target variable is binary, which has got two classes, our objective is to separate the two classes. And how good we are able to separate the two classes, we can find out using a rank order table and KS statistics. So we'll now see how to go about making a rank order table. How does your data look like? When you build a model, your data look like something composed of predictor variables, that is independent variables, and the target variable. Using the independent variable and the target variable, you build a model, and then using that model, you predict the probability for each record. In this, we are now focused on what is the likelihood of a particular record being 1. So assume the probabilities which are shown in the table as probability for 1. Okay. Once you have built a model, you have computed the probability. What is most important is how your probabilities link with the actual target. You want your model to give higher probability to records which are actually 1, and the model should give lower probabilities to records which are actually 0. That is what we expect from our model. Considering the two important columns, which is the actual target and the probability, what we will do is we should sort the entire data. Just visualize in front of you, you have your entire data set, you have computed the probability, and then you have sorted the entire data based on probability which is predicted by the model. Lower probability at top, higher probabilities at bottom. When you have this sorted data, you're scrolling through your data from low probability to high probability. As you scroll in the target column, initially you should see more of zeros occurring. And as you scroll below, as the probability increases, you want the frequency of ones coming should increase. And if that happens, in that case, your model is a good model. Now, how do I quantify this? We are not be quantifying by scrolling our data. We need a way to quantify this. So first step, what we are going to do is we are going to sort our data, say ascending or descending. Here I have shown ascending sort, low probability at top, high probability at bottom. Having sorted the data, what we are now going to do is break this data into 10 buckets. Sorted data, we are now breaking it into 10 buckets. Initial 10% of the record, let us call them rank 1, that is decile 1. Next 10% of data, let's call them as decile 2, then 3, 4, 5, 6, 7, 8, 9, 10. Deciling is a process of splitting data into 10 buckets, each bucket having approximately 10% of the total observations. Once you have created decile, can I aggregate my data at decile level? Can I say in decile 1 how many records are there, and out of those records how many ones are there and how many zeros are there? In decile 2 how many records are there, out of those total record how many of them are ones and how many of them zeros? Can I aggregate my data at decile level and create a summary? Yes, I can. So the next step in a rank order table creation is summarizing, aggregating the information at a decile level. The table here shown is a hypothetical table where in each decile I've shown 1000 records are there, and out of those 1000 customers in decile 10 295 customers have responded. I'm assuming that two classes are responder and non-responder class. So out of 1000 here 295 responders are there, then 176 responders and so forth. At bottom 7 responders. Total number of records 10,000. Out of 10,000 overall responders are 787. I request all of you to create this data in your Excel, and step by step we are going to create the entire rank order table. So copy paste these numbers in your Excel. The initial 3 columns in this table, you can see A, B, C, is what we have done in our previous step. If you know in a given decile how many customers are there and how many responders are there, can we compute the number of non-responders? Obviously, number of non-responders is equal to number of customers minus number of responders. So compute non-responders in your Excel sheet. After having computed the number of non-responders, we now need to compute response rate at each decile. Response rate is number of responders divided by total number of customers targeted. So in decile 10, we have got 295 responders out of 1000 customers. So my response rate would be 295 divided by 1000, that is 29.5. For the second decile, that is decile number 9, number of responders are 176 divided by 1000, my response rate will be 17.6. This way you have to compute response rate for each and every decile. By observing the response rate, you can see in our decile 10 my response rate is 29.5. In decile 9 response rate is 17.6, and as we go down our response rate falls from 29.5 to 17.6 to 11.5, 7.5, 3.5, 3.0, 2.3, 1.8, 1.3, 0.7. Response rate is decreasing, and this is what we expect. We gave decile 10 to customers where the model predicted high probability to response. Decile 1 was given to customers who have low probability to respond, which means expected actual number of customers in low decile should be less and more customers actually should be responding in high decile. The model is rank ordering. There is a order in my response rate, and if you get this kind of a order at decile levels, you can say your model is perfectly rank ordering. Let us consider a scenario where cost of targeting a customer is rupees 100, revenue per conversion is rupees 1500. Revenue here responders, let's assume responder is conversion. How is the rank order table useful in decision making? At an overall level, if you see, you have got 10,000 customers. If you have to target 10,000 customers at the cost of rupees 100, in that case, the cost of targeting would be 10,000 into 100, which would be 10 lakh. And you have 787 conversions. At a revenue of 1500 per conversion, my revenue would be 787 into 1500, it would be 11,79,000. Profit would be 1,79,000. Overall, if I see, the campaign is a profitable campaign. However, if I now see things at decile level, I can see each decile there are 1000 customers. So my cost of targeting would be 1000 into 100, that is 1 lakh. My revenue decile wise, if I see, in the top decile, decile number 10, I've got 295 responders. 295 responders multiply 1500, my revenue would be 4,42,000 and my profit would be around 3,42,500. If I now see decile 9, my profit would be 1,64,000. Then decile 8, 72,000, 12,000, and decile 6 onwards, I see actually I'm making loss. Once I have this rank order table in front of me, for a marketing campaign, it becomes very evident from decile number 6 onwards, I have started making loss. So really, if I have to do campaign, I should be targeting customers in decile 10 to 7. In that segment, I actually make money. And if I target only customers in decile 10 to 7, my profit would have been 5,91,500. By targeting less number of customers, I'm actually making a profit which is 3.3 times what I would have made if I would have targeted all the customers. AUC model performance measure does not help you come to this kind of profitability calculation. This kind of profitability calculation is easily done by creating a rank order table. That's why many a times, besides seeing AUC model performance measure, we end up also creating a rank order table to build strategy, marketing strategies where to target customers and where not to target the customers. We are now going to build our rank order table further. We have got the profitability calculations, we have understood it. We now move to creating our rank ordering table. Here in my Excel, I have already done these calculations. We are now going to see further calculations of rank order table. Let us build further our rank order table to compute the KS statistics. KS statistics is Kolmogorov-Smirnov statistics. Difficult to remember the full name, but I'm very clear many of you will easily remember the second part of the statistics, which is Smirnov. Okay, let us now create 3 new columns which are cumulative base, cumulative responder, cumulative non-responder. What you mean by cumulative is, if I target only the 10th decile, how many customers I'm going to target? 1000. If I decide to target the 10th and the 9th decile, how many customers I'm going to target? So basically the way you have to create cumulative is something like this. You put equal to, you put this cell, and then you have to say this one plus this one, then this plus this. This is how you have to create your cumulative column. So now I'm going to just copy paste these 2 cells and paste it below. This is how you have to compute your cumulative. Likewise, you have to compute the cumulative responders, and likewise you have to compute the cumulative non-responders. All of my numbers are already pre-populated, so kindly do all of these things in Excel. After having computed cumulative base, cumulative responder, cumulative non-responder, we have to compute percentage of those. The way percentage will be computed is 1000 divided by 10,000, then 2000 divided by 10,000. This way, this denominator 10,000 for base, total base will remain same. When you have to compute cumulative responders percentage, in that case you will have to take number of responders divided by total number of responders. So you can press F4, make the denominator constant. Then 471 divided by this number. Likewise, you can compute the percentage cumulative non-responder. What you are going to take is the number of non-responders in a given decile divided by total number of non-responders. You can again press F4, copy paste the formula. My values are already populated, so I'm not copy pasting here. Compute all of these three: percentage cumulative base, cumulative responders, and cumulative non-responders. We are now going to understand the case computation. So let us assume we have got two axes. The x-axis is percentage of population selected. The y-axis is percentage of respondents. On x-axis, if we select from the entire population, which is 10,000 observation, from 10,000 observation, I randomly select 1,000 observations. 1,000 observations out of 10,000 represent 10% of the total population being considered. Now, if I consider 10% of the total population, that is 1,000 records, in this 1,000 records, which is randomly selected, I can expect there will be 78 responders, and 1,000 minus 78 will be non-responders. 78 responders as a fraction of total responders, that is 787 in this case, will represent 10% of total respondents. So if I select randomly a 10% population, I'll capture 10% of the potential respondents. So I get a dot here on this axis, 10, 10. If I randomly select 20% of records from the population, the number of responders in this sample would be 7.8% of 2000, that is approximately 156 responders will be there, and this 156 responders as a percentage of 787 would be approximately 20%. So if I select 20% of population, I'll have 20% of respondents captured. I'll have data something like this. If I select 30% of population, I'll have 30% of respondents captured. This way, if I keep increasing, I'll have 10, 10, 20, 20, 30, 30, 40, 40, 50, 50, 60, 60, 70, 70, 80, 80, 90, 90, 100, 100. This is a theoretical line. However, because of our model, if I now go with a modeling strategy and I select only the top decile, in that case, when I select 10% of the population using a modeling strategy, I get 37.48% of responders captured. So if I now plot the modeling strategy, my graph will go something like this, not like this one, sorry. This graph will actually go at 30%. It will go something sharply like this, because in 10% of the population using modeling strategy, top 10% captures 37.48% of the total responders. If I select 20%, the graph will go from 37.48 to 60. 30% of population selected, the graph will go to 75, like this, and eventually if I select the entire 100, it has to come to 100, 100. So this is going to touch here, 100, 100, right? On this side, it will be 100. Do you agree? What will be the graph looking like if you plot non-responders? The graph of non-responders will go something like this. So this one is for my responders, the top one. The below one is for non-responders. The middle one is for theoretical line. If you can see this, there is a gap between cumulative responder curve and the cumulative non-responder curve. Somewhere this gap is maximized, and after a certain point this gap starts shrinking. Somewhere in between there is a maximum separation between percentage cumulative responders captured and percentage cumulative non-responders. That point of maximum separation between cumulative responder and non-responder is called the KS statistics, Kolmogorov-Smirnov statistics. A good marketing model should have a KS statistics above 45. Ideally, above 45 is considered a good model. You may have 55, 60, 65 also. However, if you get a KS statistics of 80 or 90, you should not be very happy because it is an indicator of overfitting. Good marketing model will have a KS between 40 to 60, 65. That means you will have a model which is not overfitting. I'm erasing the graph. This entire graph is shown here in the case chart, where I have taken those numbers, all the numbers, decile wise responders and non-responders, and I've created the graph, which is something looking like this, where you have on top axis the cumulative responders, bottom is cumulative non-responder. The point where you will have the maximum separation in this graph is the case statistics. Getting the point of maximum separation from graph is difficult. That's why we typically do this calculation here in the case column. The way you will have to compute is you have to take this cell minus this cell, copy paste this formula, and wherever you get the value which is maximum, you consider that value as your case statistics of the model. Coming back from the Excel to PowerPoint, the same table which we just computed in Excel, we have now understood the case calculation. This is the chart, lift chart. What you have to do is you have to do cumulative responder, cumulative non-responder, point of maximum separation. Final concept, which is lift chart. From the previous table, the columns which are important, which I have taken here, if I target only the decile 10, what is my response rate going to be? The response rate is going to be 29.5%, which is shown here. If I do not have a model, in that case, I would be randomly selecting the customers and targeting. In that case, my response rate expected would have been 7.9. This number is 7. 7.9 is a expected response rate. When I target only the top decile, my response rate is 29.5. How many times it is higher than my random response rate? That is 29.5 divided by 7.9 in this case, and that number would have come out to be 3.75. If I target top 2 deciles, which means I'm targeting decile 10 and 9 together, what will be my response rate and what will be the corresponding lift? Calculate. If we target the decile 10 and 9, in that case, number of responders will be 471. Total number of customers which we will target will be 2000. So my response rate will be 471 divided by 2000. That will be 23.6. It should not be 29 0.5 plus 17.6. That would be a wrong calculation. So my response rate is 23.6. How many times it is higher than my baseline? My baseline is 7.9. So 23.6 divided by 7.9 would be something 2.99. This way you have to keep computing. If I target the top 3 decile, in that case my number of responders will be 586 out of 3000. My response rate will be 19.5. 19.5 divided by 7.9 would be 2.48, like this. If I target all the decile, obviously my response rate will be 7.9. The ratio has to be 1. A good marketing model, if you see the lift, in that case in the top decile, the lift should be around 4. A number close to 4 is ideally considered good. Above 3.5 definitely it is good, but we should try to reach in the topmost decile the ratio to reach around 4. We are close to 3.75. So there are multiple ways of seeing the same model. One is the KS, other is AUC, then area under the classification accuracy, lift. A lift chart is something which looks like this, which you get. So these are various model performance measures. We are now going to see the case statistics for our model built in random forest algorithm. All the logic that we discussed of deciling, the aggregating at decile level, in rank ordering, all of those things has been codified here. So I'll just quickly run this deciling function. Having executed deciling function, to create the rank order table, this is the entire logic which is here. We have created a function. So I'm going to run the rank order logic, and I now print the rank order table. Here, if you can see, I have computed the KS for development sample and the holdout sample. On the development sample, my KS is coming as 0.61. On the holdout sample, my KS is coming as 0.4. Once again, you will say it is overfitting. No, the catch is on the model on which you built, you are using that training data to compute the KS statistics. The KS statistics or the training data has to come using cross validation. We are not using cross validation to compute the KS in the training set. As such, I should simply ignore it. You build the model on the same data, you are completely testing the model on the whole data. That's not the right way. Cross validation is the right approach of getting the right statistics. So here we'll ignore the KS statistics on the development set. My KS statistics on the holdout set is 0.4. And I know from AUC my model is not overfitting. Okay, so my case for the model is actually 0.4, that is 40 in percentage terms. We now see the rank order table. The entire rank order table is shown here. Most important, when you see the rank order, you have to see the response rate: 30.8, 14.5, 9.3, 9.3, 6.8, 3.5, 3.6. There is a marginal increase here. It should be gradually falling down. There is a marginal increase, then I have to cross check. This marginal increase is because of one record. Here there are 21 responders and here there are 22 responders. I can ignore that crack. 1.67, 2.5, again there is a crack here. Again there is a crack, 1.5 and 2.5. And finally 0.83. Either you try to overcome this crack, or you may say this crack is in the very lower decile. And from a model deployment perspective, I'm not going to target here. So minor crack coming here, I can ignore, because my deployment strategy would be targeting only the top decile. So from that perspective, you may ignore. However, if the crack would have been somewhere here in the third and the seventh and the sixth decile, I will not tolerate that. I would try to fix it. Okay. So having considered that response rate, we have to see our KS, and the KS for our model is coming as 0.40. With this, we have completed random forest technique. Thank you. You can contact me for further queries on the email ID which is mentioned here. And the other ways of contacting us is definitely on the meetups and on our website. We will see you in the upcoming session where we'll consider another machine learning technique. Till then, thank you. Bye bye.